Thank you. Thanks everyone. Thanks for taking the time. Thank you. So thanks for really appreciate taking the time to attending our talks, and especially the guys, you folks that attend in person, regardless of the stormy and rainy weather also in San Francisco. So today we have two talks from Uber. So I'm going to first talk about like Uber's big data platform, and then we have Stefan here with me, and he's going to talk about Uber's machine learning platform. I know machine learning is the hot topic, so but I'm assuming that everybody needs to bear with me for the first part before we build the data that we can use for machine learning purposes. My name is Reza Shiftafar. I manage the Hadoop platform team at Uber. And this talk is the summary of our journey over the past few years at Uber to build a large-scale big data platform. If you need to get in touch with me, I'll be hanging around after this talk so we can chat afterwards. But if you need to reach me after that, you can send me an email or you can connect with me on LinkedIn. The slides contains the links. So the agenda for my presentation is actually a brief introduction in terms of Uber's data and how data is used across different services. I'll do a quick overview of what we had as our first generation of big data platform a few years ago. And then I spend most of the time talking about what we currently have, what problem we have to solve. And I'll wrap the presentation by talking about what we're currently working on and what's coming up next. So Uber's mission is to build a platform that can ignite the world and set the world in motion. So to that end, data is at the core of the company, and almost all the services and products that we build are somehow built on top of this data. To give you a sense of how data is widely used across the company, so at any points of time, we have 500, 600 simultaneous concurrent experiments running, trying to tweak different features or try out new features in production to see which one are user-friendly and are used by users better than the other ones to roll out in scale. At the same time, we have services using this data to generate new functionality to the rest of the company. For example, the service that Uber Eats used to estimate is a machine learning model that estimates the time of delivery for each food for your food. That is basically hitting over 800,000 queries per second to update users about what time of arrival they should expect. On top of that, we have several thousand dashboards across the company that different teams use to see how the business is performing and to basically make business critical decisions based on those. To get a better sense of where we started and why we end up having so much data. So let's look at our trips growth over the past few years. So Uber started in 2010. It took us 6 years to reach our first 1 billion trip. But then we did the second 1 billion trip within 6 months. And we did the next 1 billion trip within 4 months. And we are right now doing around 1 billion trips every 2 months. And with this, you can see the slope of this curve is exponentially growing. So we should be re-architecturing our platforms in a way that we can deal with 1 billion, 2 billion trips per month, very soon. And this is not just because we are going to new cities and what we are using the Ubers. It's also because of the fact that we release new products, and these products are more sophisticated products. It creates a better user value, user expectation, but behind the scene, they generate more data because they are more complicated. So if you look at this graph that shows what main features we release over time, in early days in 2010, we only had the ride-sharing business, so it was one rider, one driver, and one trip happening at the time. Then we started launching Uber Food in 2014. That becomes a more complicated product because then you have two riders with one driver and one trip. And then in 2015, we launched Uber Eats. And again, it's more complicated than before because now you have 3 parties involved. You have the drivers, the person who ordered the food, and the restaurants involved. And if you think about it, it's actually each food delivery is actually 2 trips at the minimum because the driver needs to go to the restaurant, pick up the food, and then deliver it to the end user. Same time, we started our efforts towards building autonomous cars. Where ATG started in 2015. And these cars are having tons of sensors, so they generate huge amount of data all the time. And we are still running it in pilot test mode. So imagine if we start rolling this out at some point at large scale, how much data that's going to generate. In 2017, we started the Uber Freight. which is the service that allows different companies to ship packages and products between different cities. We also started the Uber Elevate, which is like our drones that they're the platform that allows drones to take the riders from one location to another. Last year, we launched a bunch of similar other products, including Uber Bikes. You've probably seen the red jump bikes around San Francisco. We also started Uber Scooter and also our service to give rides to the patients who are going to visit the hospitals or clinical facilities. So these services, again, they are becoming more user-friendly. They provide a better user experience, but at the same time, they also generate more data behind the scene. And we're definitely going to have more products coming up next year. So just imagine that the scale that data is going to go based on that. Internally within the company, we mostly have three categories of users. As on one hand, we have these city operators. These are the underground crew in each city that operates that city. So the way you can think about it is see it as like a small startup within Uber that manages one city. These are the folks that looks at the numbers within their city and make business decisions how they can grow in that city. So we have several, basically thousands of these folks using our data to make business decisions on a daily basis. The other category of our data users within the company includes data scientists. These are the folks that looks at the previous data. They try to find the trends. They try to try out new ideas on historical data. Basically, they try to find ways to improve the experience for based on the previous data going forward. And then we finally have different engineering teams across the company that they use these analytical data to generate a new service and generate new functionality to the rest of the company. A good example is like the service that allows any other service in the company to get an estimation in terms of time of delivery of the food, or the service that predicts the estimation time of arrivals of the rides, the fraud detection as a service. So we have so many different services across the company that they use these data to generate new functionality for the rest of the company. And we have hundreds of these services, engineering teams across the company using our data. So in terms of numbers, if you want to get a sense of like how large our infrastructure is, so we have a tripod strategy, which means we have our own data centers. At the same time, we also use clouds. So these numbers are the order of magnitude you can expect in one of our data centers. So in like one of our data centers, we have several tens of thousands of hosts, and these are having like basically virtual machines running on them. So we are having several hundred thousands of equals running on them. Our data size in our analytical data lake right now is over 100 petabytes. We have several trillion messages generated and stored in our Hadoop cluster per day. So this is like this stuff is running at extremely large scale on daily basis. In terms of how we build our software stack, so we heavily rely on open source technology. Again, the stuff that we use is like at a scale that no single company can operate these stuff on their own. So we rely on all the companies that are dealing with the same issues to work together and solve the data problems. And to this end, we use a lot of open source technology like Spark, Hadoop, HDFS, Hive, Presto stuff. But many of these technology doesn't work out of the box at our scale. So, and it's more than just reconfiguring this stuff to work. We have to look inside the codes, and many times we have to find workarounds to bypass the limitation, or many times we have to actually patch or improve some of the architecture part of them to scale it to the limit that we want to run them. And our strategy is that we try to contribute back our improvements. For example, like we worked extensively in the past 2 years in terms of scaling the HDFS name nodes. We contribute back our observer name nodes codes. But we are also working on router-based federation, and we are trying to contribute these back to the community to basically help everyone benefit from FlexSpeed. At the same time, there are gaps in the industry that there's no viable solutions out there for us to just take and use or improve. So we have to basically build some of this stuff from ground up within the company. And again, we try our best to open source them as fast as we can so that the rest of the community can help us take them to the next level. At the same time, everybody benefits from those as well. Specifically, in this talk, I'm going to talk about two of these in-house made softwares. One is called Hudi, and the other one is Marmaray. And we're going to see in this presentation why we had to build them and what problems we're trying to solve. And they're both open source if you guys want to later try them. Cool. Our team, which is the big data team, our mission is to have a reliable infrastructure that we can ingest, store, and serve all these analytical data to the rest of the company. It's a very straightforward mission statement, but to make it happen, we have to go through a lot of troubles and build a lot of technologies together. So let's start by looking at what our big data platform looked like a few years ago. This is, I call it traditional, but it's actually from 3 years ago. So this is the architecture of what we had as our big data platform back around 2015. If you look at this, so if you start looking at it, on the left-hand side, we have different sources of our data. So Kafka is used a lot across the company as a way to pass messages between different services or as a way to buffer messages for a period of time. Then we have our data sets, like our important data set, like trips and like user transactions. These are stored in sharded databases. And finally, we use service-oriented architecture across the company. So many of these services relies on some database to store the data. So we have all these data, sources of data on the left-hand side. And if you think about it, there's another part to the left of these data stores. So if you wanted to make a big picture of how the whole thing works, we have two different doors that we work. We have the online door. These are the absolute minimum number of services that are required to work properly and work with each other to let the users take a ride or order. So this is the online door. And then anything afterwards, so when Uber trips finished, that transactions get stored in one of these data stores, for example, or sharded data store. From there on, all the services are relying on basically it's called analytical board, which relies on these sources of data to study data or generate new functionality, new analysis of it. So these are the sources of our data. So we built an ingestion service. Basically, we had a bunch of Spark shells that go into different sources, ingesting all this data and bringing them into Hadoop. One early best that we put in this area was to make the schema mandatory. Because again, we expected these data to grow exponentially over time. And it's very easy to have all the data in one Hadoop data lake, but it becomes a data swamp that you can't. Everything is there, but it's not easy and accessible for users to access the data. We wanted to prevent that, so we wanted to avoid any low quality or bad data to get into our data lake. So we started enforcing schema from the very early days, and that pays a lot in terms of improving the quality of our data for our users. So when the data gets ingested into Hadoop, we store them in columnar 5 formats of Parquet. And the reason for that is like our source of data. These are wide tables. We are talking about several thousands of columns for our data sets, and they are deeply nested, 5 or 6 level of nesting. So when you bring them into Hadoop, if you store them in columnar 5 formats, it optimizes for the users to access this data in terms of their query cost, because most of the users, they're not going to run a query across all these different thousands of columns. They're mostly interested in 1 or 2 columns or a few things of these columns. And storing the data in columnar 5 formats is a perfect way of improving the query compute cost for the users. At the same time, when you store the data in columnar 5 formats, the way you are laying out the data on this is that the data of the same time are going to sit next to each other. So when the data gets compressed, you get much better compression ratio, and your storage cost goes down too. So that's the reason that we had to pick a columnar 5 formats, and the reason we picked Parquet at the time is because of its relatively good integration with Spark. So anyway, so the data gets ingested into Hadoop and stored as columnar 5 formats of Parquet. Any data modeling happens within Hadoop on top of this data. So we have ETL modeling teams that they read these source raw data and they generate, this is like a classic star schema. They read the source raw data and they generate different dimensional effects for the rest of the company teams. Another assumption that we made at these early days was to ingest the data into Hadoop in the as-is format without letting any transformation to happen. And the idea behind that was if we let users to transform data in somehow when the data is brought into Hadoop, what's going to happen if 2 different teams need 2 different transformations? Then we need to bring 2 different copies of the data into Hadoop. So one other assumption that we made in the early days is we bring the source of data into Hadoop only once, in the exact same format as the upstream source, and any transformation, we let it happen within the Hadoop on top of these data in a scalable way. So this was our Hadoop data lake. So everything, the raw data as well as the model data was landed in Hadoop. And then the users across the company, they could access these data directly through query engines like Hive or Presto that they can write basically SQL statement. Or the users who need programmatic access to this data, they could use Spark or notebooks to access this data. At the same time, we load the subset of our data, mostly the very recent sets of data, to our warehousing softwares that allows most of these city operators to run their SQL statement in a very fast fashion. So with this architecture, we were able to store a few tens of petabytes of data in a Hadoop data lake. At the same time, we were able to provide the data latency of 24 hours. Cool. So the big wins that we get out of this is this was the first time that we had all the analytical data in one place. So it basically opened doors for the rest of the company to do whatever they want. So everybody was super excited. There were more and more users trying to build services on top of this data. And it basically was the first time that we were able to use the full potential of our previous data to build new products on top of them. So it was a very big thing for us to have all this data together in one place. But at the same time, this popularity led to more and more data to be brought into Hadoop. So we soon started facing the limitations with like bringing too much data in. The first pain point that we had at the time was scalability. And this scalability has two folds. One is that we use HDFS as a file system. So HDFS is scalable when you get to a few petabytes or a few tens of petabytes. When you get to 30, 40, 50 petabytes, you're going to start seeing all the corner cases. And that was one of the limitations because we soon start hitting those corner cases and those limitations. The other limitation that we had was with our ingestion platform. So it wasn't a real platform. So we had a bunch of custom ad hoc Spark jobs that were connecting different data sources and sucking in the data into Hadoop. The problem with that is these are very fragile. It wasn't like it was custom. Someone wrote a Spark job to bring the data in. So it worked fine when we had a few tens of tables, a few hundreds of tables. But when we start having like a few thousands of tables, these pipelines were very fragile and were breaking every day. So we had multiple engineers just doing nothing but going and trying to fix these pipelines and making them work. So the data reliability was significantly affected because of these fragility. The second limitation that we faced was in terms of data latency. So we were getting the data from the source in a snapshot model. Basically, we went to whatever data store we have upstream. We made a snapshot at that time, convert everything to Parquet, bring it into Hadoop, swap the tables into Hadoop, and let users use the new data. This was working fine, but again, our data set was growing in size. So our trips table was, for example, a few hundred terabytes. So when you go and bring it into Hadoop, it takes several hours to convert it into Parquet. So it wasn't scalable. So that's why the data latency couldn't go lower than 24 hours. At the same time, our data by nature has a lot of updates, and dealing with these updates and data running data was also a big problem. Our modeling was also happening on top of these raw data that were refreshed in a snapshot way. So the model table also has to work in a snapshot model. So they need to regenerate the entire model tables every time. And this was, again, obviously not scalable and not efficient at all. So to better understand what I mean when I said our data by nature has a lot of updates, let's look at one specific data set, for example, our trips table. So the source of our data store is like basically some sharded data store at our upstream. So the trips get stored here. We have like basically a stream of these change logs from these sources coming into Hadoop, and we have a batch job that runs, let's say, every few minutes or hours, and brings this data into Hadoop. When the data gets into Hadoop, to optimize the cost of query, we partition the data based on date. So based on the date that trips happens, the data gets into one of these partitions. So for example, if you take a trip today, let's say you take a trip, the trip fare is $15, that gets basically ingested and stored into the partition. This is one of these, for example, green boxes that is the new date. At the same time, you later tomorrow look at the trips, your receipt, and say, oh, $15 is too much. The driver probably not take the optimized route. So you basically you submit a support ticket asking our team, our customer support teams to look into that. They look at that and say, oh yeah, there was a mistake, or the driver overcharged you for any reason, but they change it back to $5. Now you have an update on your previous fare. That is an update that you receive. And this can happen like for the trips that you take, usually within a few days. The other form of updates that you may have is like when you rate your driver. So you rate your driver next time that you take a trip. And if you don't take a trip on a daily basis, which I hope is no one is in that category, then you're gonna maybe rate your driver next week, next month, or sometime after that. So depending on the origin of the updates, you may get an update for a few days ago or a few months ago. And again, we may at any time end of the year arrives, and our financial team, the finance team, they try to get backfilling for some tax purposes. So we're going to have updates. So we initially were trying to find workaround and that basically hide it under the rug, but it was natural part of our data sets. So we had to find a solution to deal with that. So let me see how are we doing in terms of time. Okay, I'll go. I wanted to see how much anyway, so I'll go faster. So the reason that our data latency was remaining at 24 hours was because we get a stream of all these change logs from our upstream data store, but we couldn't bring them into Hadoop at once because again, Hadoop is append only. At the same time, we are storing the data in columnar file formats. So columnar file formats, you have to have your whole data sets in memory and then organize it and flush it into this, right? So if you get that, and we try to have large files in Hadoop, so let's say we have 128 megabytes, 256 megabytes of file. Now, there's no way you can go and update one record in that file. That file contains several thousands of records, right? So the way we were able to absorb these updates at the time was we had some technology like HBase that allows updates. So we get a stream of change log from these sources, we put them all in HBase, and we make a snapshot out of HBase every few hours, and we reconvert that data into Parquet, and we swap the tables into Hadoop. And this snapshot generation conversion to Parquet takes time. For trips, it was several hundred terabytes, and it was when we moved to our next technology, that job itself was taking 20 hours. So there was no way that we can refresh the data faster than 24 hours. So that's why the latency was still remaining at 24 hours. So let's fast forward and look at how we solve the problem and what we currently have to allow users to have access to faster data. So the main motivation for rebuilding this platform was, again, Hadoop became extremely popular and a lot of teams were using their existing data. They demanded, like they say, more reliable data. At the same time, we were seeing that the data is growing exponentially in size, so we have to think for long term. And this was the first time that we were out of those firefighting modes. So instead of like trying to gradually improve the service, we spend some time looking at our data set, what data set we're dealing with, what are the characteristics of our data set, and most specifically, what's the access pattern? How are users querying these data? And we try to build the new architecture that is long-lasting and it's going to last us a few years. So let's look at the limitation that we had and how we solved those problems. The first limitation that we had was HTTP scalability. This is like a very common problem. So everybody who starts having more data, they're going to hit it at some point. Around a few tens of petabytes, you're going to see the nameless becoming the bottlenecks. It's a painful thing to fix, but it's a lot of companies have dealt with that in the past, and fortunately, they have published their solution. So it's a straightforward way to scale that beyond that. It's hard, but it's straightforward. Again, in some way, you have to basically scale your name nodes. And many companies do that by basically clustering their data set across different Hadoop clusters. And they use some form of basically, they use UFS or federated name nodes, some way to redirect users between these clusters. And if you avoid files, small files, and you have a few Hadoop clusters, then you're going to be able to get to like beyond that few tens of petabytes. So I'll skip the details here, but we have a detailed engineering blog post on that. If you want to know more about that, I'll refer you to this engineering blog post. So the other problems that we had was the scalability issue with our ingestion platform. As I said, it wasn't a platform, it was just a bunch of ad hoc Spark jobs bringing the data in. So the way we solved our ingestion like scalability issue was to build Marmaray. Marmaray is basically a data ingestion and dispersal framework It's designed in a generic way that it can connect to any source and it can connect to any sink and it moves the data around between these two. It's very modular. It's built on top of Spark, so it's horizontally scalable, and it allows users to easily add a new source or a new sinks or basically create a pipeline of these sources and sinks. The good news for you is that it's already open source, and if you want to know more about it or using it, we have another engineering blog in terms of the details of that, so feel free to give it a try. At a very, very high level, we have so this is how Marmaray is implemented. So it has a bunch of source connectors and a bunch of sinks connectors, and between these two are a bunch of converters. And you can define any logic for your converters as long as you have a connector to get the data in and get the data out. And you can have a multiple of things to transform, massage the data, and so we started moving all our jobs from a bunch of ad hoc Spark jobs to Marmaray platform that makes it more organized. Basically, we didn't have to go and fix individual pipeline issues. We had to just make our platforms reliable and ask users to unload the data into that. At the same time, we standardized our data model in Hadoop too, and we introduced basically two sets of tables in our Hadoop. These are raw data tables. So if you think about it, we have a data store that, for example, we store all our trips data at the very top level. It's transactional data store. So there's a bunch of, for example, row 1, column 1, value A, value B, value C, value D comes here. If you think about that, so for row 1, you initially had value A, value B, and then it becomes updated to value C and value D. So when you bring this data into Hadoop, we generate two tables out of that. One is called changelog history tables, which means it gives you the history of changes per each row. So you can know that row 1 initially had value A at time t0, then column B it becomes value B. So you can see the history of these changes. At the same time, this is like a sparse table, and if someone wants to basically get the latest snapshot, they have to go and basically merge the whole thing, right? Which is very inefficient. But it has its own use cases. So on top of that, we also provide the merge snapshot tables that allows users to see the current latest values for every row. So it basically merges and compacts these tables in a merge snapshot tables. So we provide these two tables for all our upstream data sources, and this allows users to pick the ones based on their use cases. Okay, so let's focus on the other problems that we have to solve. So the other problems that we had was, okay, the data latency was too high. We were having basically snapshot-based ingestion of data that only allowed the new data to get in every 24 hours. So we had to move out of that, and we had to move to a model that allows incremental ingestion, which means we get the upstream changes, and we only bring those into Hadoop and we update our previous data rather than regenerating the whole data set just because one record upstream is updated. So that was one problem that we had to solve. The other problem was the need to address basically updates and deletes. And again, we need to be able to columnar data, we couldn't get rid of that because that's optimized for storage and query type. We need to find a way to provide update and delete functionality on top of this columnar data. And if we could do those stuff on the modeling side, the reader side, they need to also be able to incrementally update these fact and dimension tables without regenerating the whole tables. So that was basically the modeling table. The modeling part also had to move from snapshot-based modeling to incremental modeling. And the way we solve this problem is by building a storage abstraction library called Hudi. Hudi stands for Hadoop Upserts and Deletes. It's a storage abstraction library implemented on top of Spark. So by nature, it's horizontally scalable. And it basically provides you with two main functionalities, two main primitives. One, it basically allows you to perform upsert, which means having a HDFS or having a file system with a bunch of columnar files in it. It allows you to go and update, delete, or insert records without the need to regenerate it. So it gives you the upsert functionality. At the same time, on the reader side, it lets the readers, the users, to incrementally pull out only the change data. Think about our trips table. We are having several billion records there. A few new trips gets added at the end. Some of the records in the past gets updated. So users who are reading this table, for them to know what records are new or updated, the only way they could do it in the past was to do a full table scan and try to use some notion of time to find the records that are updated. with Hudi. And that, again, full table scan at that size is extremely expensive and not efficient. So Hudi, what provides is a functionality called incremental proof, which means given a timestamp, it gives you a stream of all the records that are observed, deleted, or inserted. So it's extremely useful for the users who are actually using this data too. So the good thing about Hudi is, again, it's open source, and it only relies on HDFS to operate, so it doesn't have any other dependency. We also have another detailed engineering blogs on Hudi, so if you want to learn more about that, I'll get you guys to do that blog post. So this is a very high-level overview of how Hudi works. So we have a batch of change logs that's coming in. This includes updated records or new records to be inserted. So when you get this data into Hadoop, you obviously have to store the actual data somewhere. So this is the data files containing the records. On top of that, Hudi creates an index. So next time you need to find the records, you can use this index to see what files and what partition contains that. In addition to that, Hudi also stores some metadata information in terms of what time and what records was inserted. And this is later used when the users needs to pull out only the change data rather than the full scale. So this is the high level how Hudi works. Okay. I need to move a little faster. So incremental processing is the key for the readers to be able to efficiently read the updated data in Hadoop. So think about it this way. It provides stream functionality on top of the batch data. Basically, you are running batch mode, but you can access the data. You can get a stream of change data, which makes it very efficient because you don't do the scan. And so again, if you think about traditional, for example, Lambda architecture or how different companies align streaming and batch technologies. So if a user needs data as fresh as a few seconds, the only solution they can go with is mostly like a database, a traditional database. If they need something between, for example, 1 second and 1 day, a lot of companies, including us in the past, we recommend users to use some streaming fashion. And anything, if some application doesn't care about basic data being older, not as fresh as 24 hours, then you can do your query in a very optimized way, but it's going to be in a batch way, but it's going to be dealing with the data that's 24 hours late. With Hudi incremental processing, we were able to move this threshold between streaming and batch from 1 day down all the way to a few minutes. So now we have the same thing that users who need the data within basically a few seconds and 5-10 minutes, they still need to go with streaming. But all the other users who need data between a few minutes of freshness and a day, they now can rely on incremental batch and Hudi to give them the stream of these updated records. And anything beyond that, obviously, you can fall back to your traditional snapshot-based batch. There's another examples to give you a sense of how Hudi works. So think about it, we have the same two batches of data coming in. So the first batch contains key 1, value A, value B, key 2, key 3, and some values. And the second batch that we ingest, it has an update on key 1 and a new record key 4. So if you look at these tables like this in your data store, so initially you have T1, value A, B, at time T0. Later, at some time, it becomes value H and G, and this K4 was also added later. So Hudi provides two modes to read the same table in Hadoop. One is the latest mode, which is the snapshot model, which basically at any point, it gives you the latest snapshot of these values. So if you look at this table, for value 1, you're going to see value G and H, and you're going to see K4 if you query the table at T2. At the same time, if you are having an iterative ETL jobs that keeps running some modeling or some applications, some specific query on top of these source tables, and last time you run it was at time T1, next time you want to run it, you don't want to reprocess the whole data. So you can pass in your previous checkpoints, like your T1s, and Hudi gives you only the updated or inserted records after that. So it makes it very efficient for the users to get access to these updated and new data. And this is how our architecture looks like after we introduced Marmaray and Hudi into the platform. So we get a stream of changelog from the upstream source, and we ingest these into Hadoop using Marmaray, as well as the Hudi to update the previous data. So this allowed us to bring our data latency down from 24 hours to just 30 minutes. So that's for all the raw data, and then there was 30 minutes on top of that for data modeling and all the other jobs using this stuff. So our end-to-end data latency was brought down to 30 minutes. At the same time, we by scaling HDFS and building like a relatively reliable platform, we were able to scale our data size. And this is like a very, very high level overview of like all these components put together. So we have different sources of data across the company. Our handover is across between the data source and the Hadoop cores are in Kafka. So they give us a stream of the change data, and the Marmaray bring them all into Hadoop, store them into the file formats, and users can play around with this data directly in Hadoop using Hive, Presto, or Spark. They can play over different platforms. So we have other platforms, like Stefan is going to talk about machine learning platforms. This machine learning platform runs on top of this Hadoop data, and it generates some new data. It can be models, or it can be any sets of derived data sets. And sometimes, for example, think about Uber Eats. They bring all the data into Hadoop, they run a daily machine learning model that generates a new model for recommending new restaurants. And at some point, they need to take this new model out of Hadoop back to their online data store to serve live traffic. And Marmaray allows them to get the data out of Hadoop and disperse it out of Hadoop as well. And we have a schema service on top of all this stuff to make sure the data is consistent across the whole platforms. At the same time, it makes sure that the quality of the data is matching the predefined schema by the producers. Okay, cool. So this is what we currently have. So are we done? Obviously not, because I'm still working there. So let's look at what problems are remaining and what we're currently working on to solve. So the first one is like the data quality. So data quality is going to be an ongoing battle. So it's never ending. We did a good job initially to make sure the data that we bring in are structurally safe and matching the predefined schema. But there's a problem is we enforce the schema within the analytical database. We do have an online RPC host for all these services to use, and they have very flexible schemas in that way. So there was a disconnect between the online boards and the analytical boards, and they were both having their own data schema. So one effort that we are currently working on is to bridge this gap and have one schema defined across all these different boards. That's one effort that we're working on. The other initiatives that we're working on is to move beyond having structural type checking of data and starting to define semantic checks. For example, you can define like a value in your data as integer, and it's an age. So if an age of a person, you can't have a negative number. You can't have a 1,000 value for that. So you have to be able to restrict that to a certain place, right? So we want to move beyond structural type check, and we want to be able to define semantics on the data. At the same time, the current platforms, we have 30 minutes data freshness for our raw data arriving into Hadoop. Again, it's extremely improved compared to what we had a few years ago, but that is not what the business needs. Our business still is asking different things. We're still asking for much faster data in Hadoop. So we are working on technology that lets us bring the latency down to 5 to 10 minutes, and hopefully that's going to happen in 2019. Efficiency is our big next effort. Again, at some point we want to go public, so the hardware cost is a big portion of basically our infrastructure. So we need to think about the efficiencies. Traditionally, we were using Mesos for online services for scheduling on the services, and we were using Yarn in Hadoop for scheduling of batches. Right now, one of the projects that we're working on is a project called Latency. That is a unified resource scheduler across Hadoop and online services. So it helps us basically improve our hardware utilization. At the same time, having one scheduler lets you get a better insight of what's going on, what type of hardware you need to add. Hudi is still an active project. So we implement first like Hudi Storage 1.0 that we are running currently in production. We've been working on version 2 of that, which significantly improves the performance in terms of dealing with updates and deletes. To give you a little bit, just have a few minutes. So I'll quickly go over these slides to give you a taste of what Hudi 1.0 is doing and what improvements we made last year. So the Hudi 1.0, which basically is work based on a technique called copy and write. So you get these batches of data over time, and you have row 1, row 2, row 3, and then you get updates on row 1, and you get updates on row 1, row 2. So these batches, we receive them like at time, like say every 1 hour parts. When you bring this data into data, so the first batch you get, your ingestion service, it puts it into one Parquet files. So you have all these records here. And then you receive the second batch, right? It has one records update. So the final data is written in the Parquet file formats. So there's absolutely no way to go and modify the actual file contents. So what Hudi does behind the scene is it creates a new version of that file. It copies the data over, updates that records, and versions those files so we know what versions they're in. And as you get more updates, it creates more versions of these. At some point, we go and clean up the oldest versions, but that's how Hudi works behind the scene. But I think it's clear for everyone that it lets you have the notion of updates in your ingestion platform, but behind the scene, it basically results in high write amplification because you are rewriting a whole file because of one that was getting updated. But this was like what we had at the time. So the way we solve this problem is called Hudi Storage 2.0, or a technique we call merge on read. So in this solution, when you receive these batches of data, the first batch you receive, you write it into Parquet files. But any batch that you receive after that, you don't want to rewrite a whole like 128 megabyte, 256 megabyte file just because of one record being updated. The way we deal with that is we create a raw file format, Avro file formats next to that base Parquet files, and we keep storing these updates next to the original files. When we have a asynchronous compactor that, based on some policy, goes and merges these two files and creates a new file only when we have enough updates to justify the cost of rewriting the files. And this is what this significantly helps with making Hudi more performance to deal with high ratio of updates and dates. At the same time, if you think about it, the reason we had the data latency of 30 minutes in the past is because we don't want to create a new version of the files every 5 minutes. So we basically batch it limited to every 30 minutes. So every 30 minutes, we absorb all the updates within that time. With this new 2.0 version, we don't have that limitation anymore because we are keeping adding the data in a raw file and we have an asynchronous compactor. So we can have this ingestion service running every 5 minutes. We can have it running much faster. And we can absorb the cost of writes in our compactor at a later time. So this is the main reason that we are right now that we have rolled out 2.0 in production. We are able to go and reduce the frequency of ingestion from 30 minutes, every 30 minutes, to down to 5 to 10 minutes. Cool. I think I'm out of time. Okay, so I covered most of the stuff. If you want to learn more about the details, we have multiple engineering blog posts that covers different aspects. The one that I highly recommend you guys to read is the one called Uber's Big Data Platform. It's a more detailed version of the talk I just gave. It has a lot of examples and details if you want to read it. So that's one. And then if you want to look into how our ingestion platform works, we have one detailed blog post on Marmaray, so you guys can refer to that. At the same time, we have another blog post on Hudi, so definitely refer to these three. At the same time, we are, if any of the topics that I talked about is interesting to you, we are actively hiring for our office in San Francisco or in Palo Alto. So either send me an email or send an email to this email address, or come and talk to me afterwards and we can see whether there is a good match. Having said that, I think I'll wrap it up here. Hopefully you have time to take a few questions, and then I'll hand it over to Steph.
What you just had on your LinkedIn page, because I noticed you posted these links.
Oh, I see. Oh, sure. Yeah, definitely.
Thank you.
Yeah, definitely. I'll do it. Sure. Yeah.
How do you manage one data that's partially
a very good question. So the question is how Uber manages schema evolution over time, and it is a natural part of a data platform growing. So I mentioned that we started enforcing schema in the early days, and to be able to do that, we built a service called Schema Service that uses Avro to enforce back-forth compatibility of the data as the schema evolves. The problem is it works perfectly fine in theory, but the problem is it's not like we can't have full Avro backward compatibility in practice. Avro is very generous with what it calls backward compatibility. So when you have Avro with a set of backward compatibility rules, then you have Parquet, which has a subset of those, and then you have Hive metastore, which even has like a subset of those. So what we did, we started enforcing those as restriction on top of our Avro backwards compatibility. So our schema service first make sure any schema change is backwards compatible based on Avro. On top of that, it looks at the different different restrictions that we have based on Parquet and Hive metastores to make sure it's like full time. But we still again, it's pretty stable right now, but again, once in a while you hit a corner case and you have to add that as a restrictions.
Could you say a little more about your data quality issues? How do you detect problems faster and remediate it faster?
Okay, very good question. So the question is how about our data quality and how we detect data quality issues in practice. So we spend a lot of times building a data pipelines monitoring service. It's called Nightwatch, and hopefully we can open source it sometime next year. What it does, it basically batches the data based on the timestamp, and it tracks the data across the pipelines, and it ensures the completeness, freshness, and latency of the data. Freshness is basically maximum timestamp you receive at the end. Completeness is when, for a specific time interval, you have received all the data at the end. And latency is mostly, so completeness is a relative term. You can say, okay, what's the completeness of the data in Hadoop for time, let's say 8 to 9 this morning? And I'll give you a number, it's maybe 80%, and over time, hopefully it starts growing up. So, but not all application requires 100% data completeness. So we have it a flexible way. You can query the completeness, and you can run your query based on whether that is good for you or not. Latency is defined at a certain completeness level. We provide in Hadoop data lake right now 4 nines of completeness. So you can ask certain tables and ask it to give you the latest time interval for which we have 4 nines of completeness. But we track every record that gets to our pipelines. So we have schema enforced. Because of that, a lot of data may have like corner cases that have bad schema. So we put them in a side table called error tables, but we report them as a separate metrics. So we know exactly what goes where, and we can report it back to the users. Yeah.
A few slides back, when you spoke here, you mentioned that one of the things that you added was index data file and data.
Okay.
How is that index different from the data catalog?
So this is indexing per table at the record levels. So think about, for example, your retrieves table. You have billions of records, right? That's the indexing that it provides. Good. So, and the reason for that is you have all these records, right? You partition them, but in one partition you still have a few millions of records, right? 100 millions, right? You get an update on one record, and you have to find the file that has that record. Otherwise, you can't update that. Right? And that is the index that I need. It's used at the storage level by Hudi. It's implemented within the Hudi to find the exact file that is listed on updated. And there's different ways. Even Hudi has multiple even Hudi has multiple implementation for that. It has basically a default Bloom index filter index. We just implemented, and I think we are going to write a blog post on that, a global indexing. That lets you, so Hudi right now it has a relatively good indexing to find the records, specific records within one partition. But it still it relies on users' input to find the partition that it goes to. The problem is if someone puts the wrong timestamp, you're going to go and start looking at exactly. So the global indexing solves that problem by having exactly what partition, what records, what file contains that record.
Which file not the
which file not in the file. Correct. We are still going back and forth in terms of whether the data records in the file should be sorted or not. There's pros and cons for doing that, but yes, correct. We're not exactly. But, yeah.
How do you transfer the data to other historical data? It's like you have a metadata service data, the new data come in, but if you have like a petabyte of data already there, and once you see partial format, it's not a unique format. How long does it take you to transfer the data?
Okay, so the question is, if you have an existing data set, how we convert that to Hudi? And you were specifically asking that Hudi has support for that natively. Okay, so right now, we don't have a support for that. So if you want to do that, we have tools in Hudi library that allows you to convert the data into Hudi file formats. And we did that for a lot of our historical data set that we wanted to support. For example, when we had GDPR, so we built Hudi in 2016-17 based on the nature of our data set. Later in 2018, the GDPR requirements came out that requires like all the companies to go and actually update and delete historical data in Hadoop. And we started using Hudi to enforce that technology. But because of that, there was a lot of historical data that was traditionally assumed as append-only, like Kafka data sets, but we had to convert them into Hudi data sets. So we built a bunch of tools that converts the data into Hudi file formats, but it takes some time and it takes some compute resources. We are considering in 2019 a way that you don't need to rewrite the Parquet files. You can scan them and create an index next to the files without regenerating the whole data set. It makes it much better, much more efficient, and much more scalable. It's ongoing. So it's going to hopefully coming soon. But feel free, if you're interested, we can collaborate on that.
We try to Hudi 1.1.
Oh,
that's exactly the problem.
Okay, fair comment. It's ongoing and it's coming soon, hopefully. Any other question? Yeah, sure.
You mentioned that in Hudi version 2, you have some merge between the other files and the files that happen on Marmaray. What kind of that merge?
Oh, okay. So I'll repeat the question and I'll answer that. So the question is, in Hudi 2.0, we have a base Parquet file and an Avro file next to it, and the merge is happening on the query side, right? Actually, not true. So you have a base Parquet file and you have an Avro file next to it. So there are different, so it provides two views on the same data set. One, we call it basically a read-optimized view, which means the query doesn't get the performance hit because of merging these two, which means you would only see the base Parquet file. But we also have an asynchronous compactor that compacts these two at a certain time interval. So the policy for that we do that compaction is based on when we have enough data to justify the rewriting, or every few hours.
So we'll always have a latency that is based on what
Correct. On the read-optimized view of the tables, you have that latency. The good news is most of the users who care about recent data, so the recent dates partition, that's where all the new records goes, right? So those, you're going to have enough data that you is compacted, quickly pixie, and the data gets compacted and gets exported to the user very fast. This case happens mostly when you have one record from 2 years ago that gets updated. And you don't want to go immediately rewrite a big file because of one record updated, right? So you wait for 2 hours and then do the compaction. And those are mostly in the past, so it doesn't usually fix the query that much. But at the same time, we do have basically a real-time view of the same table that does this merging on the fly. And those are the use cases that are willing to pay the extra compute cost to get access to 5 years database. It is abstracted for the user, so same tables. Again, you have everything laid out on this separately. So it's whether on the query side, the user set the flags that basically merge these two or not. By the way, that merging part, which right now it's not rolled out in production. We have the Hudi 2.0 rolled out. That merging part is what we're currently working on to roll it out in production in the best possible. Any other questions? Well, thanks a lot for taking the time and attending this talk. I'll be hanging around after, like Stefan's talk, if you want to talk to me afterwards. But again, my email is there. If you need me, send me an email or like send me a message on LinkedIn. Thanks.